Good. Okay, so the angle of deviation for red light is theta subscript r, and the angle of deviation for blue light is theta subscript b. Now, I compare the following for the red light and the blue light. And the first on the bill is half speed of light. We have to compare the speed of light for the red light and then the blue light. So, class, this is the question. We are required to compare the speed of light for the red light and then the blue light. Let me get your views. Yes, who's starting for us? Compare the following for the red light and then the blue light. The speed of light. Yes. Who is starting for us? Volunteer and answer. Mary, Anna Adwa. Let's compare the speed of light for blue and then red. The speed of the blue light and then the red light. Adwa. Adwa. Yes.
Sir, please. So I think that the speed of the red light is slower than the speed of the blue light.
So you think speed of red lights
Yes, sir.
is less than speed of blue lights.
Yes,
What
sir.
is your reason? So V red is less than V blue by Gerard. What is your reason?
Sir, please. This is because for refractive index, the more you are able to bend, how do I say, towards the normal, the higher your refractive index. So if we consider the relationship, the equation, refractive index is equals to the speed of light in air to speed of light in water, in glass, or this one. So for this one, the speed of light in this one, air is constant. But when you come here, the speed of light in this one, it varies. Therefore, you can see that the one of the red lights is much slower than that of the blue light.
Okay, that is Gerard's opinion. Yes, more views. Another view. Let's hurry up. What will you say about the speed of light of the red light and the blue light? Eliana, Gerard, Irene, Kezia, Mary, Nane Julia, and Nane Fua. We are comparing the speed of light of the blue and then the red light. Yes. Hey, apart from Gerard, nobody wants to make a contribution. Okay. Now, supposing the two rays never got deviated, what will you say about it, about their speeds? Supposing the red light, the blue light takes the same path as the incident white light. Supposing this is the case, and each color, yes, the white light was dispelled, but there wasn't any deviation in their path. What will you say about the speed of red and blue? Yes, Nana Adwa Bosan. Supposing there wasn't any deviation.
Is it to be the same?
It will be the same. Go. the same speed. But here is the case, the red light is deviated a little bit. This is the red light. And this is the blue light. Blue light. There is some deviation with respect to the first one. Then the second one, there's a wider deviation. In that case, what will you say about their speeds when you compare? So, Gerard and the class, time's sake, the speed of light of the red light is greater than the speed of light of the blue. The reason is that red is less deviated compared to blue. If there hadn't been any deviation in their path, the speed is the same. But here in the case, this is deviated, but when you compare it to blue, this is lessly deviated than the blue, meaning there will be a change in the speed of red and then the blue, but the change in the speed of the blue will be greater than the change in the speed of the red light because of the extent of deviation. Gerard, are you okay?
Yes, sir.
It's because of the extent of blue light is more deviated than the red light. All right. Now let's move on to, please take note, put some things down. Now, the next question is about, we are comparing now the refractive index. The beta question is about the refractive index. We are to compare the refractive index of the red light and then the blue light. Yes. And I'll expect one of you ladies to talk about the refractive index. With a round of applause, let's welcome Deborah to answer that. with a round of applause. So Deborah, refractive index.
Mr. Dear, please, the refractive index of the red light is greater than the blue light.
Why? What is your reason?
Mr. Dear, please, the refractive index is directly proportional to speed of light in air over speed of light in a medium. And the speed of light in the medium is
this is refractive index in terms of speed. Absolute C over V. Okay, this is speed of light in air, speed of light in a medium. In this medium, the red light has a greater speed than the blue light because it is less deviated. Okay, let me pick another view. Let me sample at least two views, then we make the conclusion. Kezia, talk about the refractive index of the red light and the blue light. Kezia, don't waste my time. Hey, hurry up, don't waste my time.
So please increase with increased speed, effective index.
Before Kezia answers, you see, the refractive index of a material is the ability of the material to deviate light compared to air. The absolute refractive index of a material is the material's ability to deviate light compared to the deviation by air. Okay. is that material's ability to deviate light, okay, when passed through it compared to the deviation by air. So what is the refractive index of the red light and the blue light? Quick one.
So it means that the blue lights will have a higher refractive index
Exactly.
than the red
The
light.
red light, because it is greatly or largely deviated. If you want to use speed, Deborah, this is that the speed of light in air is constant. Now, the speed of red light in the medium. Okay, hold on, I'm coming. Take it and go. The speed of red light in this medium, okay, is greater. The speed of red light in this medium, V red, this is large. Then this is for red. Then for blue, C is constant. What about the speed of light? Speed of blue light in the medium, VB. Is it large or less comparing VR and VB? Class, I demand an answer. Speed of light, red light in the medium is large. Speed of blue light in the medium is less. So which one will be greater here? Will it be the refractive index of red or blue? Which one will be greater? Hey, are you there?
Sir, please.
I'm asking a question.
Sir, please, blue.
Blue.
Sir.
Yes, it's the blue light because this denominator is less than this denominator. This is greater than this. Okay. And so that is how, if you want to use speed of light, that is how to judge it. Or you look at the magnitude of the deviation to also judge it. Any question? Eliana, are you clear?
Yes.
Then gamma. The gamma question is about frequency. We are comparing the frequency of red light and blue light. Let me throw this question to Ifwa, what is your opinion? The frequency of blue light and red light. Ifwa, the frequency of red light and blue light, we are comparing. Hey. Evia is singing. Okay, let me. Eduvia, what will you say? I've asked. Hello.
Please, I don't get why the refractive index of the blue light is greater.
Adwa, you just joined there.
Few minutes.
You see, the refractive index of a material is the material's ability to deviate the path of light when passed through it compared to the deviation by air. So if the material is able to deviate the path of light so well, then the material would have a larger refractive index. So the refractive index of glass is 1.5. What it means is that glass can deviate light 1.5 times that can be done by air. The refractive index of water is 1.33, meaning water can deviate light 1.33 times that can be done by air. So if the material deviates the path of light so well, it will certainly have larger refractive index. We also define the same thing, explain using speed of light. Absolute refractive index is speed of light in air divided by the speed of light in a material or in a medium. Now, red light is lessly deviated. Look at the angle. Theta are very small compared to the deviation, angle of deviation by blue light. Meaning that in terms of speed, red light has a greater speed than blue light. So VR is greater than VB. If you want to use refractive index for red light, refractive index of red light is equal to C over V. Here is the case VR is great or is greater, right? This is greater. Then refractive index of blue light, C over VB. We have this denominator greater than this denominator. So Adwa, which one will be greater? Will it be NR or NB? Adwa, Nana Adwa.
Yes, Mr. Adria.
Which one will be greater here? Will it be NR or NB? Or you are not following? Okay. Then let's come back to our frequency. So what about frequency? We are comparing the frequency of red light and blue light. Yes. Yes, Gerard.
So the frequency for both of them will be constant.
Frequency of red light and blue light.
That could be the same.
No. No. It would differ. Let me explain. Then explain what is on your mind. You see, for a wave, frequency is inversely proportional to wavelength. If we look at the rainbow colors, red, orange, yellow, green, blue, indigo, violet. The colors move with decreasing wavelengths. Decreasing wavelength. The wavelength of red color or light is equal to around 600 nanometer. Then the wavelength of blue is around 400 nanometer. So as the colors go, their wavelength decreases. Now, what is wavelength? A wave is this. It is represented as a sine function, okay? And this is, so we describe a wave to be sinusoidal. A wave is like this. When we talk about, please, are you there?
Yes, sir.
Pay attention, class, all of you. When we talk about a full wave can be two successive points that are in phase. This point is always in phase with this, or crest to another crest, or trough to another trough. Let's pick this. So A full wave has a crest and then trough. So this is a full wave. Because we haven't all done waves, let me just put it this way. This is a full wave. So we have this positive pulse and then this negative pulse, forming a full wave. So this is what we call as a wavelength. Okay. Now, when we talk about frequency, we are talking about the number of complete waves within a given time. So how many complete waves can we count? So look at this one. We can count 1, 2, 3, and then a quarter. Okay. Now, if a wave has a shorter wavelength, this is what it means. Let me draw another wave. But this time, this distance we are calling as wavelength is short. This is a longer wavelength. So this is it. So this wave has a shorter wavelength, meaning that the distance from one positive pulse to another negative pulse, very, very short. So this is a full wave. So this is the wavelength for this particular wave. Now compare it to this. The wavelength for a full wave, meaning this wave A has a longer wavelength than B. So this one has a shorter wavelength, whereas this has a longer wavelength. So let's count complete waves in this and then in this. Here we counted 1, this is 1, 2, 3, and then a quarter. Then let's count the complete waves here. 1, 2, 3, 4, and then a quarter. So this one has a larger frequency because we have a lot of complete waves in this than in this one. So what I'm teaching is that if a wave has a shorter wavelength, its frequency is large or greater. And then if a wave has a longer wavelength, its frequency is less. Class, are we okay?
Yes, sir.
Deborah and Co, are you okay? Let me get a response from all of you.
Yes, please.
If a wave has a shorter wavelength, that you can count a number of you can count adequate complete waves than a wave with a longer wavelength. B has a shorter wavelength. So when we have to count the complete waves, we have 1, 2, 3, 4, and a quarter. This wave has a longer wavelength. So let's count the complete waves. We have 1, 2, 3, and something. So the idea is that when a wave has a shorter wavelength, its frequency is high. Frequency is the number of complete waves per second. And when it has a shorter wavelength, frequency is high. If it has a longer wavelength, frequency is less. Now, look at red light. Red light has a wavelength of 600 nanometer. Blue light has a wavelength of 400 nanometer. Which of these two has a shorter wavelength?
Blue.
Blue light has a shorter wavelength. And so it implies that the frequency will be high because frequency is inversely proportional to wavelength. If wavelength is less, F will be high. If wavelength is greater, F will be less. Okay, so in terms of frequency, blue light has a greater frequency than red light. Now, however, for each particular light, if we pick red light passing through a prism, because red is monochromatic, one color, when it passes through this, it will never disperse into different colors because it is one color light. So red will be refracted, then will be deviated at the other end. But because this is one color, red light, monochromatic, its frequency will not change, okay, upon passing through the prism because it is red light. So for one particular color of light, when it is passing through one medium to another, the frequency doesn't change. But when you compare two or more different lights, then we can talk about the wavelength, the frequency of each one because they have different wavelengths. But if you pick blue light, red light individually to pass through this, the frequency will not change. Gerard, are you okay?
Yes, sir.
So for the frequency varies for different colors of light because they have different wavelengths. But for one color light passing through one medium to another, the frequency is constant. So this, okay, so I think this is how I have to explain it. Please, if you have any question, quickly ask. So frequency of one light does not change from one medium to another medium. But when you have to compare frequencies of two different lights, certainly because they have different wavelengths, their frequencies will also change. That's the whole argument. Casey, are you okay?
Yes, please.
Irene, are you okay? Hilda and Paul. Okay, now let's move on to the calculation. Yes, Mary.
Mr. Ejia, please, about the refractive index. Are you talking about the refractive index of the individual light or the medium, the glass?
You see, Mary, refractive index of a material for monochromatic light is constant. So the refractive index of glass, 1.5, has to do with when we are looking at one color light passing through. But if we have to pass different colors of light, then the refractive index would of the material would vary for red, would vary for blue, would vary for green, because these colors are bent differently. So the refractive index of a material is not constant. It is only constant when we are looking at it for one color of light. But for different colors, because different colors are bent differently, there will be refractive index pertaining to that color of light passing through the medium. Mary, are you okay?
Yes.
Yeah, please, can I see the last part?
So that's you see, 1.5 glass has a refractive index. We are looking at one white light, only white light passing through and then ignoring the dispersion. Here we are only ignoring the dispersion. So we are only looking at white light passing through this angle of incidence and then getting refracted. R, this is angle of refraction. Then we draw the conclusion that the refractive index therefore is equal to sine I over sine R. And here we don't talk about the dispersion. But if we are passing different colors of light, different colors are bent differently. And so we can have a refractive index pertaining to that color of light passing through the medium. All right. Irene, are you okay with what you are drawing? Irene, are you true? I want to clean the board.
Please, I'm coming.
Now, if the angle of incidence is 65 degrees, calculate the magnitude of theta r. We have to calculate the magnitude of theta r.
Please, I'm done.
Okay.
Please,
We have to calculate the magnitude of theta r, where theta r is the angle of deviation for the red light. Theta r is the angle of deviation for the red light. Now, let's go through some theory. So this time we are looking at for only red lights. Okay, calculate the magnitude of theta r, given that the refractive index for red lights through the medium is 1.62. Given that refractive index for red light is 1.62. So here our focus is only on the red light and not on the blue light. Okay. So it is as if we have this white light. This is the normal incident. Angle of incidence is 65. Now is deviated. Then when it comes here, it emerges through this end. And theta here is what we are looking for, the angle of deviation of the red light. So our focus is only on the red light, the reason for which they gave us the refractive index of the red light being 1.62. Okay, now in our refraction of light in triangular prism, let's refresh our memory. When it gets to this refracting plane, it gets deviated. When it is coming out of the other plane, it is deviated. When we extend this line, we have this is R1. This is the first deviation D1. If we draw a normal here, and then we extend this line gives us R2. Then we have D2. This is angle of emergence. Okay, so for one light. Now, if you recall, we equated angle of this.
Sir Adrian,
Hello.
I thought for the theta or the red light, the ray goes a bit up.
The what?
The ray, it goes a bit up.
Oh, I'm not referring to the diagram. I'm only drawing it for one. Okay. You see, I haven't drawn for the blue light, only the red.
Okay.
So angle of incidence is equal to D1 plus R1. So that when we make D1 the subject, we have I minus R1. And this gives us the deviation, angle of deviation with regards to this first refracting plane. Okay, then we can equate angle of emergence to D2 plus R2. D2 plus R2. When you make D2 the subject, you have E minus R2. And this relation also gives you the deviation which occurs at this plane. Now, this is the total deviation. This angle is the total deviation. And we realize that the total deviation dt is equal to d1 plus d2. What it means is that for one color, if we are to get the total deviation, as in this case, then we must determine the deviation over here and then the deviation over here. When we add the two deviations, we have the total deviation, which represents theta r. That's the whole thing. That's the whole thing that we need to do. So class, are we okay? Are we okay here with the theory?
Sir.
Hello.
Sir, please. When you look at it with geometry, see that the normal makes a 90-degree with the incidence ray, isn't it? So if that, we can find the angle of refraction, subtract it from 90 degrees, and then get the angle of deviation.
No, but you must, you see, this is what we are talking about. This is 90. And from here to this will be 90. Okay. So
yes,
no, it won't work like that because this part you have no idea what this is. Don't forget the 90 is from the normal, from here to the plane. From here to the plane. So if you don't know this, you cannot just subtract. Okay.
Okay.
So let's go through it. So all that we need to have to determine the total deviation is that we have to find the deviation here plus the deviation here. Then, all right, how do we do it? You see, we can use Snell's law to find R1. We can use Snell's law. So the refractive index of red light is equal to sine of the angle of incidence I, which we know, divided by the sine of the angle of refraction R1. Because we have this 1.62, we can easily find this is I is 65. So we can find sine of R1. Quickly find that for me. Quickly find sine R1 for me.
So the answer is 34.01.
Let's have a confirmation from your other colleagues. Please confirm. Who is doing a confirmation for me? Who is confirming this for me? Yes.
Please, I have a question.
Ask your question.
Please, the second diagram you drew, is it the red light diagram?
Yes, I'm only looking at it for one color of light. This one. For one color, which is the same as the question given to us.
Yes, please.
What did we get for R1? I need a confirmation.
34.0170.
34.01. Okay, so let's take 34 degrees. So once we have R1 and D1 is equal to I minus R1, we can easily find D1. So the deviation over here, D1 is equal to angle of incidence 65 minus the first angle of refraction, which is 34 degrees. So 65 minus 34.
31.
So this is 31 degrees. We need D2 to add to this. Now look at something. You see, for a fraction of light in a triangular prism, we know that the angle of the prism A is equal to R1 plus R2. Once we know A, we found R1, we can easily find R2. Okay, help me find R2.
Is R2 will be 60 degrees minus 34 degrees.
So 60 minus 34, and that is equal to what?
24 degrees, 26 degrees.
26. So R2 is equal to 26 degrees. Yes. So we have R2. We will need E. We will need E to find D2. Now, you know, you can reverse the path of light. Either you want to go from left to right, or you can go from right to left. Whichever way you look at it, it is still absolute. You can still find the absolute refractive index. So I want us to reverse it. If you want to reverse it, then the absolute refractive index of the red light will still be sine of E, sine of the, and here E becomes the angle of incidence, and R2 becomes the angle of refraction if you reverse it. So sine of E over sine of R2. It is still from air to prism, so it is still absolute refractive index. So we have 1.62 equal to sine of E over sine of, we found R2, 26. And so we can find the value of the angle of emergence. Quickly do that for me. So sine of E is equal to 1.62 times sine of 26. When you finish, E is equal to the sine inverse of all this, 1.62 by sine of 26. Yes, quickly do that for me. Let's have another person doing it so that we can be sure of the final answer. I don't want a call from only one of you. Yes.
If I had the angle of emergence to be 45.225.
Okay, let's have a seconder.
45.23.
So 45.23. Good. So once we found E, we can go ahead to find D2. So the deviation with regards to this side is equal to E minus R2. So D2 is equal to E minus R2. And 45.23 minus R2, which is 26. 26. So what's D2? What's D2?
So we should add 19.25.
Okay. Therefore, the total deviation. Hello.
I had 19.23.
Okay, so around the same figure. Therefore, the total deviation for the red light will be equal to D1 plus D2. And we just substitute whatever we have for D1, 31 plus whatever we have for D2, which is 19.25. Gerard, mute yourself. So add this for me. 31 plus 19.25. I think this is 50.25 degrees to be the total deviation of the red light. So this is the total deviation of the red light. Another method is that, you see, total deviation dt. I think I gave you this formula. dt is equal to angle of incidence plus angle of emergence minus A. Let me clear the top part, and then explain how this formula is also obtained. You see, we are saying that the total deviation is equal to D1 plus D2. Look at what the expression we have for D1. D1 is I minus R1 plus D2. The relation we have for D2 is this. E minus R2. E minus R2. So when we put them together, we have I plus E minus R1 plus R2 and I plus E minus R1 plus R2 is equal to A. So this is the formula for total deviation, okay, within a triangular prism. So if I have I which is 65 plus E, angle of emergence, which is equal to 45.23 minus angle of the prism, which is 60. I can also find it. When you add this and this, you have 110.23 minus 60. So when you subtract 110, when you subtract 60 from 110, you have 50. So 50.23, close to the same value. So this is another way to solve the same problem. Any question?
Mr. Dear,
Hello.
please, the first method, the D1, I don't understand how you equated it to 65 minus 34.
The D1. That's one.
Yes, please.
D1 is equal to I minus R1. D1, the deviation at the first plane is equal to angle of incidence minus the first angle of refraction. We use Snell's law to find R1. So sine of I over sine of R1 over here. We have the refractive index of red light 1.62 is equal to sine of 65 divided by sine of R1. Then we found R1. R1 is equal to 34. So once I have I and I found R1, Deborah, can't I determine D1?
Yes, please.
That's how we got D1. If you have any other observation, bring it up so I could explain to you, so we could move on. Eliana, all is well. Ifwa, all is well. Hey, we started with 11. We are left with 7. Adwa, Deborah, Eliana, Gerard, Irene, Kezia, and Nanadwa. Hey, Samuel. These are the things I'm not happy about. So, anyway. All right. If you're okay, can I clean it?
No, please.
Please wait.
Okay. Hurry up. Adwa, what is the problem? Adwa, what is the problem? Share. When your papa, Adwa, when your papa, who told you? You are not. Please let me know when you finish, okay? Adwa, when I did the same thing. I did the same thing. So what do you want to do? Okay, better. Wow. So different colors of light have different frequencies. This is because different colors of light also have different wavelengths. The greater the wavelength, okay, the lesser will be the frequency. And the lesser the wavelength, the greater will be the frequency. Frequency is inversely proportional to wavelength of light. So when you have to compare two different colors of light, certainly they will have different frequencies because they have different wavelengths. But when you are transmitting one color of light from one medium to another, the frequency will not change. Frequency of light does not change from one wavelength to another. But when you have to compare frequencies of light, then they will be different. So get the difference here. I gotta leave me alone. I can't be reading. Okay. I can't be reading. It's okay. about, you see, we go to, in our simple harmonic motion, we found the velocity of a body in simple harmonic motion. So for a body in simple harmonic motion, we got its velocity with respect to time to be V is equal to A omega cos omega t. This is the velocity of a body in doing simple harmonic motion with respect to time. So velocity of a body in SHM with respect to time. Then we determine the velocity of a body exhibiting simple harmonic motion with respect to displacement. So V is equal to omega times A squared minus Y squared is the velocity of a body exhibiting SHM with respect to displacement. So over here, okay, the related question is that what is the velocity of the body at a time so and so? What is the velocity of the body at a time t is equal to so and so? Girl, ladies and gentlemen, this is what you use to find the velocity when time is given. At a time of so and so, calculate the velocity of the body. This is it. Then in equation 2, at a displacement of so and so, calculate the velocity. And this is the equation or formula to use. So get the difference. Are we okay? Are we okay?
No, please.
Kezia, are you okay?
No, please. Please, I couldn't hear you properly, so I was wondering if you could come again.
How can you hear me properly when you were not around in our last meeting? We have we have two different formulas for finding the velocity of a body exhibiting SHM. The first, we have the velocity with respect to time, which is A omega cos omega t. This is the velocity with respect to time. Then velocity with respect to displacement is equal to V is equal to omega times A squared minus Y squared. This is the velocity with respect to displacement. Okay, so how do we use this one? When you are given as a period of time, you can use this to calculate for the velocity. Then when you are given a displacement of so and so, you can also use this for determining the velocity. So this is velocity with respect to time, and this is velocity with respect to displacement. Okay. For a body exhibiting simple harmonic motion, the maximum velocity of a body in doing simple harmonic motion is obtained at what point? Yes, we discussed it. Where do we obtain the maximum velocity? Deborah, for an oscillating body, where do we obtain the maximum velocity? Deborah, where?
Savior, please, at the mean point.
At the mean point. And at the mean point, the displacement is equal to 0. So if y is equal to 0, and you substitute, this is how we got it. If y is equal to 0, meaning we are at the mean point or the equilibrium position. If you substitute y there, you have v is equal to omega square root of a squared minus 0 squared. 0 squared is all this. So you end up having v is equal to this. Therefore, omega square root of a squared is a. So the maximum velocity occurs at the midpoint, and then the formula for the maximum displacement, maximum velocity is omega a. We can also use this to confirm the same thing. Velocity in terms of time is this. Now at the midpoint, the time there can be equal to t is equal to 0, or t is equal to the period. At the midpoint, t is equal to 0 when the body just is about to start. T is equal to the period is when it has made a complete oscillation from start to finish. So let's assume it is in motion. If t is equal to the period, v is equal to a omega cos omega times the time is the period, capital T. We are looking at a complete oscillation. So if capital T, we have a omega cos omega is 2 pi on t times t, this and this. So we have a omega cos 2 pi. 2 pi in degree is equal to 2 pi in degree is equal to
So 1.
2 pi in degree is equal to
360.
360. So 2 pi is equal to 360. So you have cos of 360. And the cos of 360 is 1. Therefore, V is equal to A omega. The same as what we had here. So maximum velocity occurs at the main point. Where do we have minimum velocity? Where do we have the minimum velocity occurring? Yes. Class.
Please. Sir,
Yes,
the
go
minimum
ahead.
velocity. The minimum velocity occurs
At the amplitude.
Occurs at the amplitude. And what is this value? What is this value of the minimum velocity? What
0.
is the value?
A.
No. What is the minimum velocity of a body in simple harmonic motion?
0.
Is 0. Gerard, when you finish, mute yourself. Okay, so minimum velocity occurs at the amplitude. Now, at the amplitude, y is equal to what? The displacement y is equal to what? Deborah, let me correct something. You don't say that the minimum velocity occurs at the amplitudes. You say it occurs at the extremes. There are two extremes, okay? The minimum velocity occurs at the extremes. Do not mention of the amplitude. The amplitude is a displacement, but the maximum displacement. So at the extremes, the displacement is equal to what? Class, at the extremes, the displacement is equal to
the amplitude.
the amplitude. So y is equal to a. If y is equal to a, then using the velocity formula in terms of displacement, you have omega times a squared minus y is equal to a. So a squared. If a squared, then you have omega times square root of a squared minus a squared is 0. So the lesson here, or the concept here, is that for a body exhibiting simple harmonic motion, the minimum displacement, velocity occurs at the extremes. The minimum velocity occurs at the extremes, and the magnitude, the exact value of this minimum velocity is 0. That's the magnitude of the minimum velocity.
Mr. Dua,
Hello, Deborah.
please, I can't see the screen. I don't know that maybe you are writing something on the screen.
Please, is it a general problem to all of you?
No, sir.
And Deborah, rejoin. Rejoin. Adwa,
Mr.
Adwa. So Adwa is gone. Mary has been on and off. Mina, the late Mina. Okay. Now let's talk about. I'm coming. Deborah, is it gone? Deborah.
Mr. Dia, please, it's back. Mr. Dia.
Please, can I know?
It's black.
No, it's back. Like, I can now see the screen.
Okay, it's been restored. All right. Let's talk about the acceleration of a body exhibiting simple harmonic motion. Acceleration. So the question is that why acceleration? Let's understand why acceleration. This is a pendulum ball. And now, are you there?
Yes, please.
Okay, so the body oscillates back and forth. This is the mean point. Let me draw a better mean point. So mean point. These are the two extremes. So one extreme, we have another extreme. What is the velocity of the body over here? Class, what's the velocity of the body at one of the extremes? Yes, V is equal to
0.
0. 0. You are not sure. You are a casting a lotto caster. The velocity at another extreme is 0. What is the velocity of the body over here at the mean point? What's the velocity?
It's maximum.
So V maximum occurs here. And this is equal to this is equal to
WA.
what? The maximum velocity is equal to what?
AW.
GPW.
WA.
Omega A. As it W. Omega A. Now, Gerard, are you there?
Yes, sir, Sam, yes.
Let me check ahead. Roll call. Wilhelmina, Deborah, Eliana, Irene, Kezia, Mary, and Nanadwa. Now, this is what happens. As the body oscillates between the extreme and all that, this is what happens. If the body is moving to one extreme, with the velocity, Gerard, mute yourself. If the body is moving from the mean point to one extreme, will the velocity be increasing or decreasing? If the body is moving from the mean point to the extremes, is the velocity increasing or decreasing?
Decreasing.
Pardon?
Decreasing.
So over here is a decreasing velocity. So we have decreasing velocity. That is why when it gets to the extreme, it is 0. Now, when it is moving from the extreme towards the mean point or the equilibrium position, Eliana,
Is the Adrian?
when it is moving from the extreme to the mean point, is it a decreasing situation or an increasing situation?
Increasing situation.
So increasing. Increasing. So if a body's movement is such that it is decreasing as it moves from the mean point to the extremes, and then also such that if velocity is increasing as it moves from the extreme to the mean point. Class, can't we talk about the acceleration of the body? Can't we talk about the acceleration of the body, class?
Yes.
Deborah, why do we have to talk about the acceleration of the body? Why do we have to talk about the acceleration of the body?
Mr. Officer, I think at any point when the body is moving to the mean position, the acceleration comes in because the velocity increases within that given time. So the acceleration is opposite to the displacement in direction, but it has the same.
You see, you have the idea, but the answer is that at any given time, we have its velocity changing, as in increasing or decreasing. So we must talk about the acceleration, because acceleration is rate of change of velocity with time. So we realize that as the body goes or moves on journeys, its velocity changes with time, and so there is a need to talk about the acceleration of the body. So that is the reason why we are talking about the acceleration of a body in simple harmonic motion. Please, class, are we okay?
Yes.
Yes, sir.
Now, how do we obtain acceleration? How do we obtain acceleration? Acceleration is the rate of change of velocity with respect to time. So how velocity changes with time. So it means that to obtain acceleration, we must differentiate velocity with respect to time. So differentiate velocity equation with respect to obtain acceleration. So let's represent acceleration by the letter A. A is equal to dv over dt. Don't forget, we earlier saw that velocity is equal to dy on dt. So we differentiate velocity function with respect to time to obtain acceleration with respect to time. So this is del dt of the velocity function is a omega cos omega t, what we have. Now, differentiation of this goes, okay, goes with the chain rule, a function of a function. The amplitude here is a omega, so it is not affected in the differential. So we differentiate del dt of cos omega t, and this is equal to a omega. We differentiate the daughter function, which is omega t, del dt of omega t times the differential of the mother function, which is del dt of cos omega t. Please, I'm applying this concept in mathematics, so please don't ask me to prove because I'm borrowing the concept. So a omega out, when you differentiate omega t with respect to time, it is equal to omega. So because this is also like the coefficient, so it will come out. So we have the t over the t times, when you differentiate a cosine function, it is equal to the negative of a sine function. Please, this is a formula. I'll give it to you. Okay, so when you differentiate cos, it is equal to negative sine function. This and this will cancel out. So we have the acceleration function equal to a omega out times omega in times negative of sine omega t. So that when we multiply, we have minus out omega squared times a sine omega t for the acceleration function. So this is the acceleration function with respect to time. Acceleration of a body executing SHM with respect to time. So at a time of so and so, what is the acceleration? This is what you have to use to calculate. So acceleration equation or function with respect to time, this is it. Now, At a displacement of so and so, what is the acceleration? Here, we want to connect acceleration to displacement. And this is how we do it. Displacement y is equal to a sine omega t. So when we look at this, we have a is equal to minus omega squared a sine omega t. Now this part is equal to y, isn't it? The underlying part is equal to displacement. So a therefore is equal to minus omega squared y. And this is the acceleration formula with respect to displacement. This is acceleration with respect to displacement. So when you are given a certain displacement to find the acceleration, this is what you use. If you are given a time, at a time of so and so, calculate the acceleration. This is what you use. So acceleration with respect to time, acceleration with respect to displacement. If you have any question, ask.
Ha.
Mina. Mina. Hey, any question? Deborah and Co. Are we there? Casey, are you there?
Yes, please.
Or you've been muted by the equation. Eh?
No, please.
Oh, but this is not difficult. The only thing is that you are not so familiar with the differentiation. That's the only problem. But I'm also borrowing it and applying. Okay, so try and then with time you will master it. With time you will master it. No, I want you to look at it and then tell me where the acceleration is maximum and where the acceleration is minimum. Just as we saw in velocity. Look at it.
Is from the equation, we can see that, or we can say that the acceleration is directly proportional to the displacement.
Yes.
That means that the acceleration will be bigger or greater when the displacement is equal to the amplitude.
Good. Nice observation. So, just as Gerard said, as from this relation, acceleration is directly proportional to minus of the displacement. And this is what identifies a body doing simple harmonic motion, because we saw that a body in simple harmonic motion has the acceleration directly proportional to the displacement, but oppositely directed. So this relation confirms it. So A is directly proportional to Y, but whilst A is positive, Y is negative. So acceleration is directly proportional to the displacement, but oppositely directed. Meaning that acceleration is directly proportional to displacement. So when the body oscillates and gets to the extremes, acceleration is maximum there, because A is directly proportional to Y. So maximum acceleration occurs at the extremes. So A maximum occurs at the extremes. Okay, and the formula for that maximum acceleration is equal to minus omega squared times A. Because we are using small letter a for acceleration, let's change the amplitude to capital A. It is this because at the extremes, the displacement is equal to the amplitude. So if we are at the extreme, then y is equal to A. So we change this y for A. So maximum acceleration is equal to negative square of the angular velocity times the amplitude. Plus, are we okay? Ileana, Deborah, Mary, and Co, are you okay?
Yes.
So maximum acceleration occurs at the extremes, and it is given by a minus square of the angular velocity times the amplitude. Where does minimum acceleration occur? Yes, let me pick Gerard. Let me pick Eliana's view. Eliana, where does minimum acceleration occur?
At the stream.
Pardon?
Extreme.
Eliana, it's not true. We just said that maximum acceleration occurs at the extremes because at the extreme, the displacement is equal to the amplitude. We are talking about minimum acceleration, Eliana. Where does minimum acceleration occur, Eliana?
Please, Adam.
At the where?
Is it the main point?
I can't hear you.
Main point.
At the midpoint, why? Why? And somebody else will answer. Why do you think, yes, it is true that minimum acceleration occurs at the midpoint. Why? Somebody to explain, give me the why. Okay, Deborah. Oh, Deborah, go ahead.
Mr. Dia, please, at the mean point, displacement is 0.
Exactly. Yes, at the midpoint, displacement is 0. Yes. So look at the acceleration formula. A is equal to minus omega squared y. So if we have y equal to 0, then A will be equal to minus omega squared times 0. And this is equal to 0. So minimum acceleration occurs at the midpoint, and the value is equal to, the value of the minimum acceleration is equal to 0. No ambiguity. Okay. Please, are we okay? Nanado, are you there?
Yes, please.
Okay. Casey, are you there?
Yes, please.
Hey, Priscilla just joined us. Mina.
Stadia.
Are you following? And now Afra with this one. Okay. All right. So, class, this is where we draw the curtains on today's meeting. I think we have to end here because this is something you also would need some time to go over in order to understand. So please use the time tomorrow to go over this. The next day, we'll be looking at acceleration graph how it differs from the other graphs. Okay, then we see how we can use this to solve problems. So if you have any question, quickly ask. If you don't have any question, then we draw the curtains on our meeting for today. Press la the watch. Okay. All right. So if you don't have any question, please, bye-bye. Good night to each one of you. Okay.
Thank you, Stadia.
Okay. Yo. Are you done writing? So I can off the camera. Silence means yes.
Yes,
And we are done, right?